Welcome, calculus fans, a video on alternating series. In this video, we'll see a definition of an alternating series. We'll talk about an alternating series test, and then we'll see what the remainder is for a convergent alternating series. So an alternating series is a series of the form B1 minus B2 plus B3 minus B4 and so on. You see here that the main feature is that the sign flips. So those BNs are positive, and you can see the sign flips on each one. Now, by convention, we usually take the first term in the series to be positive, but it doesn't necessarily have to be positive. We could similarly write negative B1 plus B2 minus B3 and so on, and that's an example of an alternating series too. So a test for convergence of an alternating series. Here's the test. If you have an alternating series that satisfies b sub n plus 1 is less than or equal to b sub n, and the limit as n goes to infinity of b sub n is 0, then the alternating series is convergent. Now, this first condition is our familiar condition that the positive part of the series be decreasing, and as we know, there are lots of ways to show decreasing. As it turns out, it just has to be eventually decreasing. So what that eventually decreasing means is that it technically just has to be have a derivative that's negative after a while, although usually we'll see that series are decreasing right away. Okay, so this is the alternating series test. A couple examples of alternating series. Here's the first one. Here's a series, the sum n equals 1 to infinity of minus 1 to the n minus 1 times 1 over n. So we'll make the observation that this series has form minus 1 to the n minus 1 times b sub n, where the b sub n is given by 1 over n. So all we have to do is look at that b sub n term and verify that it is decreasing with limit 0. So the nth term in the series is again 1 over n, and we see that the n plus first term in the series is strictly less than the nth term in the series. So the positive parts are decreasing, and similarly we see that the limit as n goes to infinity of b sub n is 0. So by the alternating series test, this series converges. Now, this series might look familiar to you. We know that if it didn't have the plus or minus terms, the sign flopper, it would be exactly the harmonic series. So we'll refer to this as the alternating harmonic series. Unlike its counterpart, the harmonic series, which is divergent, the alternating harmonic series converges. Okay, a second example of an alternating series. Here's a second example. The following series is the sum n equals 1 to infinity of minus 1 to the n minus 1 times the quantity n over n plus 1. So again, we'll recognize this as an alternating series. In this case, the b sub n is n over n plus 1. Now, as it turns out, this series fails the alternating series test, and it fails both reasons actually, but we'll just focus on one, namely that the limit as n goes to infinity of b sub n is not 0. So in this case, we would say that by the alternating series test, the series diverges. It turns out that the terms are not decreasing either, and you can show that pretty quickly, either using a derivative or looking at a comparison of the n plus first term to the nth term. Okay, so finally, a theorem about the remainder of a convergent alternating series. So if the alternating series, the sum n equals 1 to infinity of b sub n, minus 1 to the n minus 1 times b sub n converges, then the remainder in the alternating series, the remainder is r sub n. It satisfies a number that's strictly less than or equal to b sub n plus 1, which is the next term in the series. Okay, so in this remainder theorem, of course, S represents the actual sum of the series, and f sub n represents, again, the nth partial sum. So again here, r sub n is the difference between the actual sum and the nth partial sum. Okay, so one thing we don't have time for is adding up an infinite number of terms, but we could add up a finite number of terms and get pretty close to the actual sum of a convergent series. And this remainder theorem tells us exactly how close we are. Okay, so a quick example that illustrates the use of the remainder theorem. Let's go ahead and have a look at the error in the first 10 terms of the alternating harmonic series. Okay, so again, that series is the sum from 1 to infinity of minus 1 to the k minus 1 times 1 over k. Okay, so the sum of the series is as n goes to infinity. Of course, the sum of the first n terms, we stop at n instead. And the remainder, in having a look at the first 10 terms, is going to be bounded by b sub 11. And in this case, that remainder, b sub 11, is 1 over 11. So I've got a mistake here, 0.0909 and so on. Okay, so the remainder again is 1 over 11, so 0.0909. Alternatively, and there are a few homework problems that do this too, you could specify a specific error and then try to figure out how many terms it takes until you achieve that error. Okay, hope you've enjoyed this video on alternating series. Thanks for your attention, and we'll see you next time.